Module 17, Chapter 22. Now there is some resistance to airflow during inspiration and expiration. This resistance is going to be controlled by bronchial diameter and by pulmonary compliance. Now recall from both your respiratory lab and in the previous module that your bronchioles are muscular airways. So they do have smooth muscle in their wall, meaning they're capable of contracting and relaxing. So when you perform bronchodilation, the smooth muscle in the wall of the bronchiole relaxes, which is going to increase the diameter of the bronchioles. And just like you heard with regards to your blood vessels, if you increase the diameter, you decrease the resistance. So bronchodilation increases your diameter and decreases your resistance to airflow. Bronchoconstriction, on the other hand, results when the smooth muscle in the wall contracts. The contraction of the smooth muscle decreases the diameter of the bronchiole, which increases your resistance to airflow. Now, let's talk a little bit about pulmonary compliance. Pulmonary compliance describes the expandability of your lungs, basically the ease with which your lungs expand, or the change in lung volume relative to a given pressure change. Now, hopefully all of you have what's called high compliance. High compliance is the healthy state of your lungs, meaning it's very easy to both fill and to empty them. However, things happen. There's chemical exposure, muscle paralysis. There are things that do happen, and these things can decrease your compliance. So if you hear that a patient's lungs have low compliance, it means that greater force is needed to expand and or empty the lungs. Now, compliance can be affected by three different factors. The first is the actual connective tissue structure of your lungs. Recall that surrounding the alveoli of your lungs, you have numerous elastic fibers. And these elastic fibers have the ability to stretch as you inhale, but then when they recoil like stretched rubber bands during exhale, they help you to push air out. However, what if you lose those supporting fibers? What if you have a loss of that natural elasticity? This is easily caused by any kind of alveolar damage. For example, menthol cigarettes. The menthol flavor is actually due to fiberglass shards. And these little needle-like bits of fiberglass can enter your lungs and actually puncture the alveoli. And all of that damage could replace the nice stretchable elastic tissue with fibrous scar tissue that doesn't have the ability to stretch or to recoil well. So losing your normal healthy supporting tissues can decrease your compliance. You also have to factor in surfactant. Surfactant is a phospholipid mixture that is naturally produced. It coats the insides of your alveoli, and its purpose is to decrease surface tension within your alveoli. And this decrease in surface tension prevents alveolar collapse with an exhale. And by keeping the alveoli partially inflated, by preventing the collapse, it makes it a lot easier to expand the alveoli with inhalation. So for this, what I would encourage you to do is find a balloon in your house, one that has never, ever, ever been blown up before. So you get this brand new balloon, and when you take your first breath and blow it into that balloon, I want you to note how much force you have to put in to that breath to create that very first stretch to the walls of the balloon. However, once you have managed to stretch the balloon with that initial breath, note that every breath you take after that, it becomes easier to stretch the balloon. So a partially inflated balloon is a lot easier to inflate than a completely collapsed balloon. And that's what the surfactant is doing. It's maintaining that first breath so that when you inhale, the balloons are already partially stretched. Now, if you don't have surfactant, what ends up happening is every time you exhale, all 300 million alveoli collapse. So you end up in a situation where you have to breathe. You have to inhale with force every single time in order to get those balloons open. This is what happens with premature infants that are born prior to the production of surfactant in the lungs. When they're born, their muscles are very poorly developed because they are premature, and every time they exhale, all of those little alveoli collapse, making it harder to inhale, and they don't have the musculature to accommodate that degree of force. Luckily, they do have surfactant therapy for premature infants that greatly helps with maintaining respiration. But not having surfactant definitely decreases your compliance. You also have to think about mobility of your thoracic cage. You learned that your ability to inhale relies on muscular contraction. So as long as your muscles are functioning normally, you can successfully expand your thoracic cage. However, what if you have muscle paralysis? What if the nerve supplying the diaphragm was damaged and your diaphragm can no longer contract? You would lose 2/3 of your resting inhale volume because of that muscle's inability to contract. So anything that would negatively increase the mobility of the cage would definitely decrease compliance. All right, now let's turn our attention away from the movement of air in and out of your respiratory structures and focus in on the actual act of gas exchange and how those gases are transported in the blood. Now, gas exchange itself is governed by two new gas laws. You have Dalton's law, which is going to describe how gases move down pressure gradients, and you have Henry's law, which is going to talk about how air partial pressure and solubility of gases relates to their diffusion. So let's start with Dalton's law. According to Dalton's law, in a gas mixture, now remember, mixture means that you're going to have different types of gases present. It's not just one gas. So in a gas mixture, each gas exerts its own pressure and contributes to the total pressure of the mixture, which means each individual gas exerts what is called partial pressure. Now, partial pressure is abbreviated with the capital P, and you can see the little subscript X. Now, that X is not for a particular gas. This is where you would put the symbol for the gas that you're referring to. So P with a subscript O2 is the partial pressure of oxygen. A P with a subscript of CO2 would be a partial pressure of carbon dioxide. So partial pressure is the partial pressure of the gas in the mixture. Now, if you wanted to calculate the partial pressure of a gas, you would need to know two things. You would have to know the percentage of that one particular gas in the mixture, and you would have to have the total pressure of the mixture itself. And then you would have to multiply the percentage of the gas you are looking at by the total pressure. Now, partial pressure is going to be important in this module because it's partial pressure that's going to determine the movement of oxygen and CO2 during gas exchange. Now, earlier I introduced atmospheric pressure, and that atmospheric pressure was 760 millimeters of mercury. We're going to expand on that a little bit now, because atmospheric pressure is actually a mixture. Your atmospheric air is not made out of one type of gas, it's made out of several. Now, what's interesting is if you break down your atmospheric air, oxygen and CO2 are not the majority. It's actually nitrogen gas that is the most abundant gas in the mixture. It makes up about 78.6% of your atmospheric air, meaning it contributes 597 millimeters of mercury in pressure to the atmospheric air. Oxygen comes in at number 2 with a pressure of 159 millimeters of mercury, so oxygen is about 20.9% of your atmospheric air. Water vapor comes in as number 3 with about 3.7 millimeters of mercury of pressure, so it's about 0.5% of your atmospheric air. And believe it or not, carbon dioxide gas comes in at the low end with only 0.3 millimeters of mercury in pressure, meaning it only makes up about 0.04% of your entire atmospheric air. Now, why do you think oxygen and CO2, that you would have more oxygen, less CO2? Now, this and the ability to understand it comes from what kind of your biology background. On Earth, you have plants and you have animals. And animals are going to take oxygen from the environmental air. They're going to use the oxygen to make ATP, and they emit CO2 as waste. However, there are more plants on Earth than people, or animals in general. And your plants take carbon dioxide from the air and release oxygen as their waste. So because we have more plants than animals, you have lower CO2 because your plants are using up the CO2, and oxygen is higher because the plants are emitting that as their waste. Now, if you start thinking about these pressures and then start looking inside the lungs, and then you're going to hear me use pressures in upcoming slides, they're not exactly going to match the numbers you see here. So the partial pressures of alveolar air are different than the pressures in your inspired or inhaled air. And there are a few reasons for this. Remember, when you inhale, your conducting division is going to humidify your air. So the air in your alveoli actually has a partial pressure of water vapor that's about 10 times higher than atmospheric air. You also have to factor in that the fresh air that you inhale is going to mix with what is called residual air. This is air in the respiratory tract that's not exhaled. And this air has higher CO2 and lower oxygen. So when your fresh air comes in and it mixes with that residual air, your oxygen partial pressure is going to get diluted, meaning it's going to decrease, and the carbon dioxide partial pressure is going to be enriched, so it's going to be elevated. You also have to remember that alveolar air exchanges oxygen and CO2 with your blood. Now, because of all of this going on, the partial pressure of oxygen in your alveolar air is only about 65% of what you have inhaled, the partial pressure of CO2 is actually almost 130 times more than the pressure of the inhaled air. So I don't want anyone being thrown off when I start talking about the pressure of CO2 and the pressure of oxygen in the alveolar air, and the fact that they don't match the values with regards to the air in your environment. Now, always keep in mind that the partial pressures that you do hear, though, will determine the movements of your oxygen and CO2. So any changes in partial pressure will directly impact your ability to gas exchange. Now, the second law that we're going to have to contend with gas exchange is Henry's law. And according to Henry's law, at an air-water interface, so that means where air touches water, the amount of gas that will dissolve into the water, meaning it moves from air into water, is determined by the solubility of the gas in the water. So will it even mix well with water? And its air partial pressure. So if you think just about partial pressure, increasing air partial pressure will cause you to increase the amount of gas dissolved in the water. So think of air pressure as pushing down on the surface of the liquid. And the greater push you have, the more gas you can push into the liquid. So increasing pressure pushes more gas into the liquid. If you decrease pressure, the gas is going to want to leave the water. It's going to want to go back to where it came from, which is your air. So decreasing pressure makes less gas dissolve in your liquid. However, it's not that simple. You have to factor in, does the gas even want to mix with water? How hydrophilic is it? Or how hydrophobic is it? And if you increase the solubility of your gas, you'll actually have more gas dissolve in the liquid. However, if you decrease the solubility of your gas, less will dissolve in the liquid. So how gases move between air and liquid, it's a really complicated scenario. But I did want to give you two examples of how Henry's law plays a role in your real life. And one way it does play a role is with your carbonated beverages. What happens at the packaging plant is you have the liquid mixture for your beverage. So the water, the flavorings, the dyes, these are all mixed together. The liquids are then put into the bottles or the cans. And the bottles and the cans are still open. And then what they're going to do is they're going to push those open containers into a chamber and seal it. And what they're going to do is they're going to increase the partial pressure of carbon dioxide in the air surrounding those containers. And by increasing the oxygen partial pressure in the air, you can force more carbon dioxide gas into the liquid within the bottles or within the cans. So you're going to get more gas in your solution. Once there's enough gas in the solution, they seal the container. So they put the bottle cap on, they seal the lid to the container, to the can, whatever beverage you've got, or the plastic bottle top. And what that does is it locks that high gas pressure into that container. So when you go to buy your soda at the store, you don't see, it's just a clear liquid. You don't see any bubbles in it as long as it's sealed. However, when you bring the bottle home and you pop the top or unscrew the cap, do you ever hear that little hissing sound? It's like shh. And all of a sudden, all these bubbles form seemingly out of nowhere inside the bottle. Well, what happens is when you pop the top, you decrease your carbon dioxide partial pressure. You decrease it down to atmosphere, which is extremely low. And if you have a low partial pressure of gas in the air, the gas is going to want to move from the liquid back out into the air. You're going to have less gas dissolved in your liquid. So what happens is the gas actually goes from being dissolved in the liquid back into its gaseous form, which forms the little bubbles in the bottle, and then those little bubbles come up to the top and pop, and it just releases the CO2 back into the air. So all those little bubbles are just bubbles of carbon dioxide gas. Now, for some people, those bubbles enhance the taste of the liquid. Um, a lot of people don't like flat soda. Flat soda is just missing the carbon dioxide gas, which is why they call it flat. There's no bubbles. Now, within the health science field, there is a therapy called hyperbaric oxygenation. And this is when they actually take the patient and they put the patient into a hyperbaric chamber and subject their body to a higher pressure of oxygen partial pressure. So they actually have the person breathing air with a much higher partial pressure of oxygen, which is actually going to force more oxygen to dissolve in their blood. So it increases the oxygen content throughout the entire body. And this is going to help your patient deal with a lot of different physical issues. For example, it will deal with anaerobic bacterial infections. The bacteria that cause tetanus and gangrene are anaerobic, and anaerobic bacteria thrive in low to no oxygen environments. So if you suddenly increase oxygen content throughout the entire body, you're creating an environment with the potential ability to kill these bacteria that can't live in a high oxygen environment. You can use this to treat various heart disorders, to help improve oxygenation. Someone who has had carbon dioxide poisoning, this is a way to force more oxygen into their blood. Gas embolisms, cerebral edema, which is brain swelling, bone infections, if you've had someone who had smoke inhalation, patients with severe burns, someone who's been asphyxiated. It's just ways of getting more oxygen into the body to help support the activity that you need to do to help battle the burns or the smoke inhalation. All right, so let's talk about alveolar gas exchange. In alveolar gas exchange, we're going to be moving oxygen from your alveolar air into your blood and carbon dioxide from your blood and into your alveolar air. Now, owing to how the gases are moving, these processes are referred to as oxygen loading and carbon dioxide unloading. Now, the reason it's called oxygen loading is we are loading oxygen into the blood. Now, with regards to the pressure gradient that's causing this loading, the partial pressure of oxygen in your alveolar air is 104 millimeters of mercury. The partial pressure of oxygen in your pulmonary capillaries is 40 millimeters of mercury. So air is going to want to go from the high in the air to the low in your blood. Now, this is going to happen so rapidly and so completely that the alveolar air actually moves so much oxygen that when blood leaves the pulmonary capillaries, it actually has a partial pressure of 104 millimeters of mercury. Now, if you were to tap into your pulmonary veins, take a blood sample out of the pulmonary vein and look at the amount of oxygen that's in there, The partial pressure of oxygen in the pulmonary veins is only 95 millimeters of mercury. Now, the reason it's a little bit lower than what's leaving your pulmonary alveoli is because the blood leaving your alveoli mixes with blood leaving non-exchange areas. Remember, you have two divisions in your respiratory system. You have a conducting division, which does not do gas exchange, and a respiratory division that does. Now, the blood leaving the respiratory division has a partial pressure of oxygen of 104 millimeters of mercury. The blood leaving the conducting division does not. And when that oxygen-poor blood mixes with the oxygen-rich blood, the overall oxygen partial pressure dilutes a little bit, meaning it lowers a little bit. Now, the reason your carbon dioxide movement is referred to as unloading is we are unloading CO2 from the blood, meaning we're going to take CO2 out of the blood, dump it into the air, get it into the body, get it out of the body. Now, the pressure gradient that accommodates this is a gradient of, in the pulmonary capillaries, a partial pressure of CO2 of 46 millimeters of mercury, and an alveolar air partial pressure of only 40 millimeters of mercury. So your blood is at 46, your air is at 40. And that's going to facilitate the movement of carbon dioxide from your pulmonary capillaries and into your alveolar air. Now, there are different variables that can affect alveolar gas exchange. For example, changing your pressure gradients. Now remember, the word gradient means a difference between two areas. So we're looking at the degree of difference between your alveolar air and the blood in your pulmonary capillaries. If you increase the pressure gradient, meaning you increase the difference between those two areas, you will increase your rate of gas exchange. However, if you decrease the pressure gradient, meaning you decrease the difference between the two areas, you're going to decrease your gas exchange rate. You also have to factor in gas solubility. Now, with regards to solubility in water, carbon dioxide gas has the greatest solubility, meaning it's easier for CO2 to dissolve in water, your plasma. In fact, carbon dioxide gas has a 20 times greater solubility in water than oxygen. And oxygen is 2 times more soluble in water than nitrogen. Now, this difference in solubility, believe it or not, is going to make sure that you have equal amounts of both oxygen and CO2 exchanged. So even though carbon dioxide has an extremely low partial pressure, much lower than oxygen, there's actually more CO2 dissolved in your blood plasma because CO2 just likes the water better. It's a lot easier for CO2 to dissolve in plasma, so even with a low pressure, its higher solubility allows for you to put more in the watery environment of your blood. Now, if you think about nitrogen, nitrogen has the highest partial pressure at sea level. However, very, 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 very little dissolves in your blood plasma because nitrogen has an extremely low solubility. At sea level pressure, there is not enough force or push to get nitrogen to dissolve in the water. Now that is great for you unless you go to do some deep sea diving. And as you go deeper in the ocean, there's an increase in pressure on the body. And as you dive, you can actually, because of the higher nitrogen partial pressure, you can push more of that gas into your blood. And nitrogen gas has an interesting effect on your brain chemistry. It actually creates a feeling of intoxication. They call it nitrogen narcosis, and you actually start to get giddy. It's like you're drunk underwater, and that's potentially hazardous because if you start to lose your faculties because of this intoxication effect, you could accidentally take your mouthpiece out and drown, make a bad decision while you're underwater, get stuck in a cavern and not realize it. So it is potentially hazardous. However, unless you are going to go diving at sea level and higher, the nitrogen issue is not going to be a problem because it just will not dissolve in your plasma. Membrane thickness plays a really important role in alveolar gas exchange. Your respiratory membrane, as you recall from the last module, is made out of two simple squamous epithelia with a very thin basement membrane in between. This respiratory membrane is only 0.5 microns thick, so there's very little obstacle for diffusion with this membrane. Your membrane surface area, remember from the previous module, you have like a whole racquetball court worth of surface area in your lungs. And increasing your surface area definitely going to accommodate a high level of exchange. You also have what's called ventilation-perfusion coupling. These are your physiological responses that are going to help to match airflow to blood flow and match blood flow to airflow. For example, let's talk about how you could match blood flow to match airflow. So you have an area of the lungs that has a low partial pressure of oxygen. So the air in your alveoli is lower in O2 due to poor ventilation per se. The low partial pressure of oxygen actually triggers vasoconstriction within the arteries supplying that lung region, meaning less blood is going to head into the low O2 area. However, in the areas of the lung that have high oxygen partial pressure, you're going to trigger vasodilation, meaning you're going to increase blood flow to those areas. And what this particular effect is going to do is it's going to help you reroute blood to better ventilated areas to help maintain adequate gas exchange. Now you can also adjust your airflow to match blood flow. For example, if you have decreased blood flow to a lung region, you will trigger bronchoconstriction. So that means your bronchioles are going to constrict, meaning you're going to have a decrease in airflow to areas where there is less blood flow. If you don't have a lot of blood flow, it means that you would have less diffusion in that area. However, in areas that have greater blood flow, you would have bronchodilation, meaning your bronchioles would dilate, they decrease in diameter, you'd have more airflow heading into that area. And that's what you want. You want more airflow to where you have more blood because it'll allow for better gas exchange. Now, let's talk a little bit about your systemic gas exchange. In systemic gas exchange, we're going to be moving oxygen from blood and into your interstitial fluid, and we're going to be moving carbon dioxide gas from your interstitial fluid and into your blood. Now, because of the nature of how the gases are moving, systemic gas exchange is going to involve oxygen unloading and carbon dioxide loading. Now, the reason it's oxygen unloading is we're going to be taking oxygen out of your blood and moving it into tissue. So in your systemic capillaries, your oxygen partial pressure is 95 millimeters of mercury. Your blood oxygen, your tissue oxygen partial pressure, is 40 millimeters of mercury. So blood is 95, your tissue is 40. So that means oxygen is going to want to move from the blood in your systemic capillaries and into your interstitial fluid. Now, with the carbon dioxide, we're going to be loading CO2 into your blood. So we're going to be adding CO2 to your blood. And the reason this happens is because your interstitial fluid has a carbon dioxide partial pressure of about 46 millimeters of mercury. Your blood carbon dioxide partial pressure is 40 millimeters of mercury. So based on this pressure gradient, CO2 is going to want to move from your interstitial fluid and into your blood. Now, at rest, which is what we've been dealing with, hemoglobin only releases about 22% of its oxygen as it's passing through a body tissue, which means that the blood leaving resting tissues through your veins is still about 75% saturated with oxygen. Now, the amount of oxygen that is actually released is called your utilization coefficient. The venous reserve of oxygen is the oxygen remaining in your blood after passing through the capillary bed. So at rest, your utilization coefficient is the 22% that is released into your tissue. The venous reserve would be the remaining 75% still in your blood. Now, oxygen and CO2 do have limited plasma solubility, so they do need assistance for transport throughout the body. So we're going to focus in on your oxygen transport first to finish out this module, and then we'll pick up in our next module with our CO2 transport. Now, when you're thinking about oxygen transport, 98.5% of the oxygen that you carry is bound to the heme, specifically the iron ion, within your hemoglobin. Remember, it was one oxygen molecule bound to the iron in one heme, meaning you have 4 hemes per hemoglobin. So that means one hemoglobin can carry 4 molecules of oxygen gas. And remember, there are 280 million hemoglobin molecules per red blood cell. And then there were, so remember from exam number 1, just how much oxygen we're really talking about here. Now, if 98.5% is bound to the hemes, that means 1.5% of the oxygen you transport is actually carried in your plasma. That is reflecting the very, very poor solubility of oxygen gas in water. Now, there have been some terms that you have heard, both in lab and in lecture. There's oxyhemoglobin and deoxyhemoglobin. Oxyhemoglobin implies that you have 1 or more oxygens bound to the hemoglobin. Deoxyhemoglobin means that there is no oxygen bound to the hemoglobin. You're also going to hear me use the word affinity in the upcoming slides. Affinity is the tightness with which hemoglobin binds oxygen. So it's how tightly the hemoglobin is holding on to the gas that it's transporting. So if you hear that there is an increase in affinity, that means that there is an increase in the tightness to which hemoglobin holds oxygen. And that means something. If hemoglobin is holding oxygen in a kung fu grip as tightly as it possibly can, it means that there is a decrease in oxygen release. So less O2 is being released from your hemoglobin for diffusion into your tissues. If you hear me say that there is a decrease in affinity, that means hemoglobin is loosening its grip. It's not holding the oxygen very tightly. And if you have a decrease in affinity, you're going to increase your oxygen release and more O2 is available for diffusion into tissue. Now, depending on your backgrounds, you might have heard the term hemoglobin saturation before. Hemoglobin saturation is basically saying here's the percentage of the hemes in hemoglobin bound to oxygen. So if you say that someone is fully saturated, it means all 4 of the hemes are bound to oxygen. If you hear that the blood is partially saturated, that means not all of the hemes are bound to O2. So if you're watching a TV show or working in a clinical setting and you hear them say that the blood is 80% saturated, then only 80% of their hemes are bound to oxygen. If they're 90% saturated, 90% of their hemes are attached to oxygen. Now, what we have to contend with at this point is how does your hemoglobin know when to release the oxygen and when to hold on to it? So you need to imagine that you are this little hemoglobin and you're traveling through the blood through a body tissue. And all you know is what your environment looks like. You can read how much oxygen is in the area around you, how much CO2 is in the area around you. You can see what the pH of the area around you is. And it's these environmental clues that are going to tell your hemoglobin to either let go of the oxygen or to hold on to it. So as we start talking about the factors that affect your oxygen transport, you need to think in those terms, that what you release or what you don't release is based on the environment, okay, that your hemoglobin finds it in. Now, one of the factors that will affect your hemoglobin affinity is actually the partial pressure of oxygen in the tissue around that blood vessel. So the hemoglobin is basically looking at the oxygen level in the area that it's in. And what you have up on the screen is what is referred to as an oxyhemoglobin dissociation curve. Along the x-axis, so coming across the bottom, you have the partial pressure of oxygen going from 0 to 100, and you can see that they've marked on that grid the partial pressure of oxygen in your systemic tissues, which is 40, and the partial pressure in your alveolar air, which is 104, but they capped it at 100 on the scale. Along the y-axis, you have your percent oxygen saturation. And what this curve is showing you is how much oxygen you can hold on in your hemoglobin at these different partial pressures. So now I mentioned with your alveolar gas exchange that with your alveolar air being at 104 millimeters of mercury, that you have such efficient gas exchange that the blood leaving your pulmonary capillary is actually at 104 millimeters of mercury. That would be 100% saturation. And if you look at the chart here, at 100 millimeters of mercury, you can see that your saturation is at 100%. That means your hemoglobin is holding the oxygen with the tightest of all grips. It's releasing nothing, and it's holding 100% of what it can. However, as you move, so the higher your partial pressure of oxygen, the more O2 you can hold. However, look what happens to your percent saturation as your oxygen partial pressure declines. The lower your partial pressure of oxygen goes, the more oxygen you actually end up releasing from your hemoglobin. So if we go from your alveoli to your systemic tissues at 40 millimeters of mercury, you notice how your percent saturation has decreased by 22%. That's because your hemoglobin reads its environment and it sees that the surrounding oxygen pressure is at 40. And that 40 tells your hemoglobin to let go of 22% of the oxygen it's carrying, because that 22% is what your tissues need to survive. If your partial pressure declines even more, you can see that as your pressure of oxygen declines, you start to release more and more oxygen for your tissues, meaning your saturation becomes lower and lower and lower. Now, this relationship between oxygen and saturation is really important if you think in terms of inactive and active tissues. So let's think about an inactive tissue first. An inactive tissue is not really doing anything. It's some muscle that's not contracting. It's adipose tissue that's not building fat. It's a tissue that doesn't have really a high oxygen demand. So in an inactive tissue, which would be 40 millimeters of mercury, that is your standard inactive tissue partial pressure, your hemoglobin doesn't release a lot of oxygen. It releases only 22% of what it's carrying, just enough oxygen to support the activity your tissues are doing to keep the cells alive. However, if your tissue changes from being inactive to active, meaning you go from resting muscle to actively contracting muscle, active tissues have greater oxygen demand. That means they're using up oxygen faster than in an inactive tissue. And active tissues can have local oxygen partial pressures as low as 15 to 20 millimeters of mercury. Now, if your hemoglobin moves into an area where the partial pressure is only 15 to 20, your hemoglobin is going to be triggered to release greater amounts of oxygen so that you can supply that tissue with the higher level of oxygen that it needs. There are other factors in addition to this that will affect your oxygen transport. Temperature. If you increase your temperature, hemoglobin actually releases more oxygen. If you decrease your temperature, hemoglobin releases less oxygen. Now, again, try not to compartmentalize this. Think about this in terms of active versus inactive. An inactive tissue is using less oxygen to make ATP. And that means they're using their ATP very slowly, meaning their heat production is lower. So if you have a tissue that is inactive, it has a lower temperature. And that lower temperature is another factor that tells the hemoglobin, hold on to what you have, I don't need it. However, active tissues tend to have higher temperatures. They're using their oxygen faster to make ATP, and they're using their ATP faster to support their activity. And ATP use creates heat. So having an organ with a higher temperature, it's a way of telling your hemoglobin, we're active here, release more oxygen, we have to make more ATP. Another factor that affects oxygen transport is called the Bohr effect. Now, the Bohr effect is more pronounced in your systemic tissues, where your oxygen partial pressure tends to be lower, so this doesn't have as much of an effect with alveolar gas exchange. Now, in the Bohr effect, as your acidity increases, now remember, an increase in acidity means that your pH is decreasing. As your acidity increases, your affinity for hemoglobin decreases. So that means that as you become more acidic, your hemoglobin loosens its grip on its oxygen and increases oxygen release from the hemoglobin. Now, you might be wondering, where is the acidity coming from? Well, the major acids that come into play with the Bohr effect are carbonic acid, which is an acid formed during carbon dioxide transport, and lactic acid, which is a waste product produced during vigorous muscular contraction. Now, you might also be wondering why in the world this happens. Well, hemoglobin actually has the ability to buffer hydrogen ions. It can buffer acid. So as you start to have this increase in acidity, your hemoglobin starts to bind the hydrogen ions in an attempt to manage the pH. However, remember, hemoglobin is protein. And back in A&P1 you learned, if you change the shape of a protein, it can't do its job anymore. It loses its function. So if you bind hydrogen to hemoglobin, you change the shape of the hemoglobin, meaning it can't do its job anymore. It can't hold on to the oxygen as well. So as your hemoglobin is buffering your pH, it weakens the bond with the oxygen, and it ends up releasing more oxygen into the environment. Now, the reverse is also true. If you increase your pH, there's less hydrogen ions available, so you're not doing that buffering job. And increasing your pH increases your affinity of the hemoglobin for oxygen. So that means you're going to hold on to the oxygen more tightly and not release as much. Now, again, it's a tricky concept, but you can also take the Bohr effect and think in terms of active and inactive tissues. Active tissues release more CO2, and carbonic acid is part of carbon dioxide transport. So if you have a tissue making more CO2, there's more acidity there. If you are an active muscle, you are producing more lactic acid. And that acid is going to affect your hemoglobin and trigger more oxygen release. So the high CO2 and the high levels of lactic acid are screaming at your hemoglobin, we need more oxygen, and the buffering effect allows you to release it. The last factor affecting diffusion is BPG, which is short for bisphosphoglycerate. BPG is a product of red blood cell glycolysis. Now remember, your red blood cells produce their ATP solely by glycolysis. They don't use aerobic respiration. Now, as BPG levels increase inside the red blood cell, the BPG binds to your hemoglobin. And if you take that big BPG, bind it to your hemoglobin, the shape of your hemoglobin changes, and it's going to end up decreasing its affinity and more oxygen is released. Now, temperature does have an effect on BPG production. Increasing temperature increases BPG production. Now think about that. Didn't we on the previous slide say that increasing temperature indicates an active tissue? So having a high level of BPG indicates potentially an active tissue, a tissue in which we would want to release more oxygen to support our activity.